Right, so we had ended our discussion on bus operations. So if we wait for others to come in, we can just make a rerun of the bus operations. So we're saying in bus arbitration, there will be a request issued by a device. Then the arbiter will check the request and see if there is no other device using that system, that bus. Then after that, you can proceed to allocate it time to use the bus, right? So we're saying we've considered the ordinary cycles, but we realize that there are also some other cycles like bus operations which involve transfer of blocks of data, and also that timing also is shown as in the diagram. Then we also talked about the need for interrupt handling. We're saying that signal which a device gives to show that it is requesting it to use the bus, or to show that it is using the bus, or to show that it is used up its own time or is finished using the bus. Those are now handled as interrupts by our interrupt handling devices, which are also chips which are used for that. So those controller chips are widely used, and in IBM systems, they normally use the Intel chips for interrupt handling. So when that happens, it handles the interrupt either by giving or telling the device to wait for its turn so that it can also access the bus. So when the CPU is able to handle the interrupt, it sends back a pulse to the interrupt handling device. At that point, the chip will specify which input caused the interrupt by outputting the input's number on the data bus. Then the CPU will use that bus in the index table to point to the interrupt vectors to find the address of the procedure to run to service the interrupt. So that is what happens. An interrupt is given, then the device address is given to the CPU, then that will also go to a vector table which shows what type of procedure should be executed in accordance with the interrupt that we have been received. So we have the CPU, then the interrupt lines, then this will be the interrupt controller, then it is a table of the interrupt requests. So if it's from a clock, it knows what subroutine to run. If the keyboard, disk, or something, then it would know which subroutine to run in order to handle the interrupt. So that is the issue of interrupt handling. Again, I'm saying most of this will go in detail when we talk about operating systems. So in short, we can say a bus is a collection of wires with a common purpose. But specifically, we're saying it's an electromechanical set of lines which are used to transfer information within the CPU or between the CPU and other devices. And so each wire is called a line. So any wire on the data bus is called a line. So in other words, buses carry information from one place to another. That's like the ordinary buses that we have. So when you look at that bus, see that there's the printer, mouse, and the like, which also use ports. And so those ports are now connected to the buses. Remember I said you can use multiplexing, so that using the same line, you can address the printer, the mouse, the keyboard, or the modem. Then there's the CPU involved, and then there's memory also involved. And all this is external bus. And the bus inside this CPU is called internal bus. Then we have also the bus controllers, which also enable communication with other controllers like the disk controllers, the graphics controllers, the network card controllers, and so on and so on. So that all those lines in black will form our system bus. So the types of buses that we can get, if it's point to point, like a serial port, from serial port to a modem, that's a point-to-point bus, or from control unit to a different logic unit, that's the point-to-point bus. Then there's a multi-point bus, which can connect different computers, right? Or it can connect from the CPU to memory, disk controller to video controller. That's a multi-point bus. Then there's also what is called a daisy chain bus, in which the bus goes into one device, and the other device will also take the information to the other device until we reach a terminal point. That is called a daisy chain bus. Then in the computer, there is the data bus. We describe that again in detail, the address bus and the control bus, right? So you realize that the motherboard, it has different configurations, but all in all, they should satisfy the basic structure given by that bus. So because we have the CPU, it has to communicate with memory, right? It has to communicate with input-output devices. And then there should be a line for control. So that tells us how the basic system bus should look like. Data bus, address bus, and control bus. Those should be there. They can either be multiplexed or in different lines, but those functionalities should be present in the bus. So if you look at the data bus carries information between the CPU and the input-output devices. Right? Carries data between the CPU and the input-output devices. That is a data bus. So the word between, it means data can move from the CPU or to the CPU. Hence, it is a bidirectional bus, right? So when data is transferred out of the CPU, it's a write operation. When data is transferred into the CPU, it's a read operation. So write operation, data is coming out. Like when I'm talking, I'm writing to you. In other words, I'm feeding information to you. That's a write operation. A read operation, I use my ears or the eyes to take information from the outside world into me, then that's a read operation. In typical sizes, 16, 32, 64 lines, some now have 128 lines. Then the signal names are normally given D something, D0, D1, D2, etc. Right? Then we have the address bus, which carries an address from the CPU to memory. This is unidirectional. Information only moves from the CPU to the memory, which means this memory, it gets the addresses from the CPU. The input-output devices also get addresses from the CPU. In other words, the CPU is the only device which supplies the addresses. That's why we are saying it's unidirectional. It's one way out of the CPU. And normally the signal lines are given A, A0, A1, A2, and so on. Then we have the control bus, which is a collection of signals for coordinating CPU activities. That makes the control bus. It coordinates the CPU activities. And each signal has a unique purpose, and the size can range from 10 to 20, and so on. So what are the signals? The signals are output, input, or they can be bidirectional, which means the signal lines are also bidirectional. They can do the read, write, clocking, interrupt, request, and so on the control bus. That's why I was saying we need a control bus, data bus, and address bus. And we're saying that's our functionality should be there. So we said the data bus bidirectional, address bus is unidirectional. Addresses come only from the CPU. Then the control bus is also bidirectional. So basically, that's what we have as for now. And as far as the system bus is concerned, right? Then let's go back to what we've talked about today and see if we have any questions which you might need. So you can now unmute your device and then we can discuss. Hello, any questions?
Say I got one.
Yes.
I wanted to find out when we are talking about the universal bus, we are talking about like something like a certain component within the CPU.
Universal bus, like
Yes.
USB.
Like I'm still trying to understand. When we're talking about the bus, what is it exactly that we are talking about? Because we are used to just the USB and the like, and then when we talk about the bus, which has got now ports and different things like that, it becomes like something which is of a new world.
Okay. It's just a terminology for wires. You know an electrical circuit, Andy?
Yes.
An electrical circuit basically use connecting wires, right? So that
Yes,
when you send a signal from one point, it gets to the next point, right? But now
yes.
what we are looking at when we are talking about the bus, now we're just talking about the connecting wires inside the computer or on the motherboard. In basic,
okay.
all those connecting wires and any other electronic equipment used so that data can move or information can move from point A to point B, that is the bus, like our Zupco bus, right? We have our Zupco
Okay.
bus. It carries people from Chavalala to town into Nast to where, Andy? But then
Yes.
all those buses that we have in Zupco, we can call them the connecting lines now. Then the Zupco system now becomes our system bus or what we call our transport system, Andy.
Yes.
So that is basically what we are talking about. That in our transport system, we have dedicated buses. We have a NAST bus, right?
Yes.
A bus will not carry someone who is not a NAST member of staff, right?
Yes.
Then that tells us about when we are talking about the memory, the data bus and the address bus and the control bus. We are saying if it's a control signal, let's say a control signal is the NAST staff, he has to go to the NAST what? NAST bus, right?
Yes.
Someone is from let's say Beggars Inn. Let's say Beggars Inn is our data bus. That person is data. That person is Beggars Inn. He goes to the Beggars Inn staff so that what we don't have confusion when information is traveling from one point to another. So basically, when we're talking about the bus, we are trying to explain the movement of information between computer components on the motherboard. All those connectors make up the bus, but then I said the signals from some of the chips are not powerful enough to travel the physical distance between devices and still keep their integrity.
Okay.
So because of that, that's when we're saying you might need a bus driver, which can sense the small signal, amplify it to a magnitude that can be sensed by the next component. So that's what we're talking about when we're talking about the system bus.
Okay, thank you, sir. I think now I understand. I can now go through the lecture again and be able to understand what was going on. Thank you very much.
That's fine. Any other questions? Any other questions? So we have no other questions. Can we end it here? All right, thank you. I'll post the two on YouTube so that you can proceed from the point where we left. Then we meet again same time next week.